Okay, so today, if you've ever wondered, how does McDonald's know that a Big Mac is 550 calories? Today, you're going to find out. What do we call the part of chemistry concerned with the study of the heat flow that occurs during chemical reactions? In other words, the study of how much energy is released, how much energy is absorbed. We call it calorimetry. Calorimetry. Now, what science is an extension of this science? Yeah, nutrition science. How do they know? They use calorimetry. 550 calories. That's actually like 1/4 of all you need for your entire day if you're a boy. If you're a girl, it's probably a 1/3. One Big Mac is 1/3 of all the energy you need for the whole day. Now, it's not include the French fries, okay? Now, if I show you a video, it's because I think the video does a better job of explaining things than I do. So you better pay attention or take notes or whatever.
In thermodynamics, we're constantly trying to measure these quantities of energy that go in or out of the reactions. The question should come up, how do you trap energy and measure it? I mean, moving from out of a reaction, where does it go? How do you catch it and how do you measure it? Calorimetry is the answer to this. It's actually a pretty clever technique. What we do is we take a substance that we know very well how it responds to heat. Our favorite is water. And we're basically going to run a reaction and let all of the heat out or in from that reaction go into the water. What we do then is we measure the water's change in temperature, which allows us to figure out how much heat went into the water. And then we conclude, that heat came from the reaction. So we know exactly how much heat comes out of the reaction. Now, it does require a little bit of planning ahead. You have to build yourself a calorimeter. Now, we have two types of calorimetry. We have constant pressure and constant volume calorimetry. I'll start with the easy one. Constant pressure is the easy one. We'll get to the volume in a minute. Constant pressure calorimetry, we also call it coffee cup calorimetry, which will help you remember that it's super easy to make. When we say coffee cup, what we really mean is a cheap styrofoam cup. Heck, go crazy, get 2 styrofoam cups and stick them in each other. You've got yourself the perfect coffee cup calorimeter. Fill it up with some water, maybe put one of your reactants in. Maybe you put some acid in it, so it's got acid floating in your cup of water. Now take some base, have a thermometer in it, and pour it in. Stir. That temperature will change, especially if you do something like hydrochloric acid plus sodium hydroxide. It's an exothermic reaction, so therefore it gives off heat, and sure enough, the temperature will rise in that solution. And it's real easy to measure the start and the finish. You look at the thermometer before, pour it in, stir, look at it when it stops. You've got yourself a delta T. From that delta T, you simply multiply that by the heat capacity of the water, which is 4.184 joules per gram per degree C, and you multiply it by the mass of the water, which you can easily weigh by sticking it onto a scale. Put all that together and you've got your amount of heat, which we call Q. That amount of heat is what was released from the reaction. That's an extensive property. We know the amount. Now you divide it by how much stuff you used, the amount of heat per gram or heat per mole, and you've got yourself the answer to the actual reaction you just ran. That's coffee cup calorimetry. Easy, cheap. Let's shift to constant volume calorimetry. We call it bomb calorimetry. It's the classic way we measure combustion reactions. It's our favorite thing to put in a bomb. Why do we call it a bomb? Well, you take a stainless steel container, you put something highly flammable in it with a lot of oxygen, and you screw the lid on really, really tight, and then you ignite it. Technically, that's what you do when you make a bomb. Now, for us, we don't want it to explode, so we make sure we don't use enough material to blow the thing to bits. But we do use enough to make it get really hot inside, but the volume is set. So because the volume can't change, there's no work done, which means all the energy is dissipated as heat into the surrounding water. Only problem is it's going to cost you a little more this time. Because now you need big container of water, you need the stainless steel bomb, you need something to spark inside the bomb, basically a spark plug, you need wires on it coming out, you need a stir bar, you need all that apparatus hooked together. Oh yeah, an oxygen tank, you got to put the oxygen into the bomb. But once you have all that and you've measured all your quantities, it's no different than the coffee cup. You push a button, it sparks, the reaction goes off, all the heat dumps into the water and the temperature climbs. Once again, you've got a change in temperature that you can change into amount of heat. That's the basis of calorimetry. It works for bomb, it works for coffee cup, and that's how we get the values of delta H for a reaction and we get delta E for a reaction. So you'll see lots of problems in your book on calorimetry, and it's a really powerful technique on how we get all these values in thermodynamics.
Okay, now, so let's say you're a nutrition scientist and you're really curious about the Big Mac. Well, what you would do is you would take a Big Mac, put it in a blender, okay, add water because you want to make it into a soup, and then until it makes it into this watery soup. Then you put it in a dehydrator, which takes all the water out. So all you have left is Big Mac powder. Take a small sample of that, put it in here, add oxygen, clamp it shut, ignite it. The Big Mac will literally, that powder will catch on fire. And as it catches on fire, it releases energy. This water here will absorb the energy. And then you measure the temperature of the water. Yes, Alec?
Does it matter how much of that powder you use?
Yes, you need to know exactly how much, because a Big Mac may be 550 grams, whatever. So if you know that 1 little gram of it gave off this much energy, you can extrapolate it out to an entire Big Mac, because you can't measure the entire Big Mac. And that is calorimetry. Now, the key thing you must understand is that water acts like a blind person's hand. Does anyone here have a friend who's blind? Okay, how does he know how you look, or she?
My mom.
Your mom is blind?
Yeah.
Really? Okay, I've met your mom. I didn't think she was blind. Cool. Okay, so how does she know what you look like?
Well, she's got a little bit of vision, so
Yeah.
she'll sort of, tell
A completely blind person, how would they get a mental picture of what you look like?
by, like, touching.
Yeah, touching you. They can't see you, okay, so they touch you in order to get a feel for what you look like. They create a mental picture from touching you. We can't see what goes on in the bomb, but who tells us what happens? The water. So if the water goes up by a certain amount, well, then we can measure how much energy the water absorbed. Where did that energy come from? Bam, came from the Big Mac. Okay, so the water, our water, is going to be kind of like a blind person's hands. So what device is used to measure the exact amount? Calorimeters. We will be using styrofoam. That fancy one we won't be using. So we won't be using that one. We'll be using this one. Okay? Our calorimeters were donated by Chick-fil-A. They were very generous. I asked them, hey, can I have some calorimeters? They said, yeah, how many do you need? And I said, like a class set of 30. And so hey, I'll tell you right off the bat that, the calorimeters were proudly brought to you by Chick-fil-A. What 3 things must you multiply in order to calculate heat flow? Mass, change in temperature, and specific heat, what he called heat capacity. The equation, which can be found on your homework, is Q is equal to mass times change in temperature times S, or sometimes is written as a C, a big fat C, for heat capacity. I like to call it specific heat. Now, be careful. Change in temperature, we always like to go from initial to final. Well, no. Change in temperature is going to be final minus initial. So it's the final temperature that it attains minus the initial temperature. And SH, or big C, is specific heat. Specific heat. Okay? So hopefully you got all those pieces. Why do we care only what happens to water? What's water to us blind people? Our hands. So since we can't really see what's going on, whatever happens to the water, the opposite happens to the reaction. Is anyone here in physics? No one here you're in physics? You understand this. In physics and in chemistry, pluses and minuses do not mean where it's at on the number line, right? A minus is not something that's on the negative side of the number line. No, a minus means direction. A plus means direction. So, if you have a plus Q, that means energy is absorbed. If water absorbed an energy, then the reaction must have given it off. So from now on, you need to think of pluses as energy going in. And that's not too hard if you think of energy as being money. If money goes into your wallet, is that a plus or a minus? Plus. If money goes out of your wallet, is that a plus or a minus? Minus. Okay, so let's talk about this specific heat. Specific heat is the amount of heat energy required to raise 1 little gram of a substance by 1 degree Celsius. How much energy is required to take 1 little teeny little gram of a substance and have it go up by 1 little degree of Celsius? Every substance, whether it's a compound or an element, will have its own unique specific heat. So like density, if you can figure out what it is, if you can figure out what its specific heat is, then you can figure out what it is. Specific heat for water is 4.18 joules divided by grams Celsius. I will allow you to take out your periodic table, which should be out already along with a calculator, and put that down on the bottom. Just make sure you don't write it really big. It's going to be that's the only space you have, and you're going to be putting more information down. So either 5 o'clock or 7 o'clock, you've got some spaces there. Specific heat of water is 4.18 joules over gram Celsius. Joules over gram Celsius. That's a fraction. 4.18 joules is on top, and grams and Celsius is on the bottom. And some of you, like Stefan there, is sitting there going, 4.18, that's a really small number. Actually, that's wrong, Stefan. 4.18 is huge. It's monstrous. Most things are far smaller than that, Stefan. You ought to know that by now. Let me give you an example. Here you have 10 grams of ice, 10 grams of iron, both at 0 degrees Celsius. Everything's the same. The only thing that's going to be different is the specific heat. So I'm going to give them both 500 joules of energy. Bang! Ah. The temperature of the water has not changed. Iron is at 114 degrees Celsius. Goes from 0 to 114 in 500 joules. Let's give it some more energy. Water is basically going, what? Are you doing something to me? I can't feel it. Are you doing something to me? Iron's going, I'm hot, I'm hot, I'm hot. 227 degrees Celsius. Another 500. Water's going, I'm feeling slick. What's going on? Iron, 341 degrees Celsius. 500 joules. Yeah. Water's going, I'm feeling kind of wet, but has the temperature changed any? No. Iron is about ready to melt. What does that tell you about water's ability to absorb energy as compared to irons without changing temperature. Okay. Putting it another way, anything like iron that heats up quickly has a low specific heat. Anything like water that heats up slowly has a high specific heat. So you're writing that down. Think of that wonderful pool that we have across the street. Come April, they will start pumping water from the Arctic Ocean into that pool, right? I mean, it has to be in order for come July, that water is like 20 degrees Fahrenheit. They start pumping water from the Arctic Ocean. So all of April, it's sitting there collecting heat from the sun. All of May, it's sitting there collecting heat from the sun. So that on opening day, June 1st, you run out there, dive in, and you turn into a popsicle. Because that water is cold. How can it possibly be cold if it's been collecting heat for 2 months? Because it's water. Water has a high specific heat. And not only that, but it's a ton of water. So how much energy is it going to take to raise the temperature of that water, which needs to be raised by 50 degrees Celsius? How much energy is going to take? A lot. So June, it's hot as blazes here in East Tennessee. And by the end of June, early July, the water is just cold instead of freezing. It's just cold. All of July, finally, by the third week of July, I decide I'm going to go visit the pool, because by the third or fourth week of July, after 3 months of sitting there absorbing energy, it is finally cool. Instead of comfortable, it's just cool. You'll get used to it after a few minutes, right? Yeah. And then, by the time, in theory, and by this time, guess what? The water would probably be warm, but it's been closed for a month and a half now. Actually, if they were to leave it open and you were to dive in October, I bet you anything that in October, after having several cool nights, it would probably be warmer than it was in June. Why? Because it takes a few months for that water to warm up till it's comfortable, Noah, and then it takes a few months for it to cool back down. That is why we are now in the peak. Even though we're just a week away from fall, we're now in the peak of hurricane season. Why? Marie?
The hot air and the cold air are starting to mix.
No. Why? Simon? That's right. Now, after all summer and spring, it warming up in the Caribbean, now it's finally warm enough to produce hurricanes. And it will be able to produce hurricanes into even October. Even though things are cooling off, the water is still warm enough. Because if it takes water 3 months for it to warm up, it's going to take 3 months for it to cool down. Here's the other ultimate example. You may want to write this down. Making chocolate chip cookies that Mr. Marino would like. This is the wrong way to do it. Take an aluminum pan. Why aren't you writing things down? Write them down. Take an aluminum pan. No, don't write this down because it's wrong. Take an aluminum pan with a low specific heat. Low specific heat. Put the cookie dough on there. Put it in the oven. Now, think about it. What cooks the underside of that cookie? The pan. What cooks 3/4 of the cookie? The air. Air specific heat is actually pretty high. Aluminum pan specific heat is very low. So, you look down there and you go, oh, it's still soft and gooey and moist on the top. It's not ready yet. What's it look like on the bottom? It's done on the bottom. It's ready. It's ready to come out on the bottom. But the top is not ready because the air hasn't warmed up enough to cook it. So by the time the top is ready, what's happened to the bottom? So then you chip it off the aluminum pan It crumbles up into little pieces. You put it in a bag. You bring it over to Mr. Marino. Mr. Marino goes, hey, we can play hockey with it. Well, don't I get extra credit? No! These are hockey pucks. I don't eat hockey pucks. This is what you should use. You should use a baking stone. Why? Because the Pampered Chef baking stones have a specific heat which is close to that of the specific heat of air, Morgan. So as the air is heating up, the pan is heating up at the same rate. So if the top of the cookie is ready, the bottom is just as ready. So then you carefully scoop them up with the spatula, put them on a paper plate, very quickly put a plastic bag, put it in a plastic bag, zip it up so all the moisture stays there, and then bring them to me. And you never know, when I'm grading your lab report, I'm eating that cookie, I'm going, this is a really good cookie. 40! Next! Now you know how important specific heat is. Plastic. Plastic. High or low? High. Think of what you're sitting on. You can still feel the heat from the last person's bottom, right? That means that the specific heat of the plastic chair is high. Copper. Low. Does anyone have any copper pots at home? Then you must be rich, because copper pots are very, very, very valuable. They have a low specific heat. That means they work great as pots, but most of us can't afford them. Steel, we can afford. Okay, so most of us have steel pots. They also have a low, not as low as copper, but low. Wood, high. Have you noticed that most spatulas have a wood or plastic handle? The spatula itself may be metallic, but the handle is wood or plastic. Oil. Does oil take a long time for it to heat up? Cooking oil or a short time? Cooking oil. Who's ever cooked? No one here cooks?
I have.
It takes a long time. If you work in a food, if you work in a fast food restaurant, baby, you better get, if you're going to start cooking at 10:30, then you have to get there at maybe 5:30 and turn on the oil, because it's going to take 3 or 4 hours for it to be warm enough to cook. Alcohol, actually low. It'll evaporate. If it evaporates very quickly, you know it's low. Yes?
So is that where when like there's cooking shows and the chef like pours wine on a pan and it just bursts in flames?
Yeah, and what you want is, what he's going for are the taste in the wine, not the alcohol. He wants the alcohol to go away, and it does. Okay, but what he wants is the taste. How about perfume? Girls, do you want the guy to smell it, or do you not want a guy to smell it? You want him to smell it. So if you put it on there and it takes all day for it to gain enough energy to evaporate, guess what? He's not going to smell it. No, you want to put it in there and you want it to evaporate and go up the guy's nose and for him to go, ooh, you smell good. So you want it to have low. Glass is high. How about on a hot day? Touch the window. Touch the window and it's still cool. Here's some other, notice that it gets even more complicated. It's not just specific, this is specific heat of water, but the specific heat of ice and the specific heat of a gas, steam, is going to be different. So yeah, every pure substance will have at least 3 different specific heats. Yes?
So, take what we were doing before with the ice melting. When the ice is partially melted, wouldn't that sort of compromise you're trying to find?
Yeah, I simplified it. But you still got the concept. Yeah, you're right. Okay, look at gold. Would that make even better pot? Yes. To tell your parents that a gold pot will work much better than steel. Okay, let me show you how easy these things are, and then I want you to try them. If there's some, you should be able to get at least most of these. They're that easy. Q is equal to mass times change in temperature times specific heat, or little s, whatever. Determine the amount of energy, that's Q, in joules, required to raise the temperature of 7.40 grams of water. What's that? From 29 to 46. What's that? Okay, is it 29 minus 46 or 46 minus 29? Watch your sig digs. They didn't give you the specific heat, but do you know the specific heat? Look on the back of your best friend. What happens to the grams? What happens to Celsius? So it's as easy as 7.4 times 17 times 4.18. Go. Please, let's get this one done at least. Ah, 520. Not only that, but there's something else that you must include. Plus or minus.
How do you know if it's plus or minus?
Well, it was a positive number. If it was 29 minus 46,
It would be
All right, so notice that the sign in the previous example was positive. What does that mean? It's positive because the final temperature was higher than the initial temperature. That gave you a positive number. Why was it higher? Because the water absorbed energy. So if it had been opposite, if the water had released energy, then its final temperature would have been lower than its initial temperature, giving you a negative integer. Therefore, you would have ended up with a negative Q. So what does that mean? Negative Q, exothermic. Positive Q, endothermic. Remember the analogy. Your wallet. If money goes in, it's positive. If money goes out, it's negative. That's a good way to remember. All right, let's try another example. What quantity of energy is Q, is required to heat a 10-gram piece of iron? That's M. And they give you the specific heat of iron. That's big C. And here is your initial temperature from, that's the key word, from, to 46. That is your final temperature. I think we have everything we need. Q is equal to M times C times delta T. Q is equal to 10.0 grams. Specific heat, 0.45 joules per gram C. Remember that units are your best friends. Final temperature, 46 degrees, minus initial temperature, 25 degrees Celsius. Grams cross out, Celsius cross out. The only unit that's left is joules, and you know what? That's exactly what you're trying to find. So, with my handy-dandy calculator here, I go 10.0 times 0.45 times 46 minus 25 is, oh my brain, 21. 94.5. A positive 94.5. Remember, that positive is important. That positive in chemistry doesn't just tell you where you are on the number line. That positive tells you that your energy is going in. It is endothermic. It gives you direction. Example number 3. Mass. The metal has the appearance of gold, so it may or may not be gold. We don't know. Requires 5.8 joules. That's Q. Not only that, but since it requires, that means it's probably positive Q. To change its temperature from, that's Ti, to Ts. Is the metal pure gold? And they gave us the specific heat. So, here's our equation. Q is equal to mc delta T. Do they give us Q? Yes, in this case they do. A positive 5.8 joules. Do they give us mass? Yes, they do. 0.6 grams. Do they give us specific heat? Now, wait a second. Some of you guys are going to jump and go, yes, they did. 0.13. We see that is a specific heat of gold. We don't know whether this thing is gold or not. It may or may not be. So what are we going to have to do? We are going to have to determine whether it is gold or not. We're going to have to solve for X. We're going to have to solve for specific heat. Remember I told you that specific heat is a physical characteristic. Not only that, like density, it can help you identify what the thing is. So, do we know final temperature? 41 degrees Celsius. Initial, 23 degrees Celsius. Bam. Alright, so 41 minus 23 is 18. So 5.8 divided by 1.6 divided by 18. Okay? So notice the units. Joules, grams, Celsius. With sig digs, I get a specific heat of 0.20 joules per gram Celsius. That's the answer. What should be the answer? 0.13. Aha! Is it gold? No, it is not gold. How much energy is lost when a solid, how much energy, that's Q, lost, that means it's negative Q, when a solid aluminum ingot with a mass of 4,110 grams cools from Ti to Tf. And there's my big fat C. Pretty straightforward. Q is equal to mc delta T. How much energy? So they're looking for Q. Mass. Specific heat. Remember, never consider specific heat when it comes to sig digs. Consider them to be truth statements. That means they are an infinite number of sig digs. And 25.0 to, remember, 2 minus 660. That's going to give you a negative number, which makes sense. 660 degrees Celsius. Okay, so let's do the math. 25 minus 660. That's a negative 635 times 0.902 times 4,110. And I get incorrect sig digs. Actually, the calculator says 2,354,084.7. And you know that's wrong. It needs to have 1, 2, 3, 1, 2, 3, 1, 2, 1, 2, 3. 3 sig digs. So it should be 2 negative. Alright? One more. And this may be the toughest one of them all. Suppose a piece of iron with a mass. What's that? That's M of the iron. Fe is the symbol for iron. You're going to learn that soon. So that's mass. at a temperature, so that's Ti, is dropped into an insulated container of water. The mass of the water is, that's another mass. This time it's the mass of the water. And its temperature before adding the iron is, that's Ti, that's before. What will be the final temperature? So they're looking for Tf. How odd. How strange. Specific heat for iron is 0.42 joules per gram C. That's something that you need to have. How odd. Okay. Let's think about it. Got a beaker and it has water in it, and you have a very, very hot piece of metal at 100 degrees C. You're going to drop it in here. Can you hear the sizzle? Yes, there's going to be a sizzle. As the water absorbs the energy, some of it actually boils away. There's going to be a sizzle. Obviously, the temperature of the iron is going to go down. The temperature of the water will invariably go up. How much energy does the iron lose? Don't know. How much energy does the water gain? Don't know. But according to the law of conservation of energy, the amount of energy that the metal loses is going to equal the amount of energy that the water gains. So you may think, well, this is easy. If you're looking for the final temperature, it should be the average between the two temperatures, 120 degrees C. Okay, that would be correct if you were dealing with the same substance and you had the same amount of each substance. You're not. You're dealing with iron, which has a very small specific heat. That means it cools down and heats up very quickly. Water, on the other hand, cools down very slowly and warms up very slowly. So, when you get something with a high specific heat and a low specific heat, they're not going to meet in the middle. This guy's going to cool down, cool down, cool down, and water's going to warm up, warm up, warm up. So if it's 20 and 100, I'm thinking the number is going to be somewhere between 20, let's see, around 22. That's my estimate. Okay, how do we do this? I'm going to have to write really small. Keep in mind, negative Q is equal. That's for the metal, the iron, is going to equal positive Q for water. If we were to replace those Q's with the equation, then that means negative mass times C times delta T for iron equals positive mass times specific heat times delta T for the water. So all we have to do is plug and play. Algebraically, this is kind of tough, but it really isn't anything but algebra 1. All right, what is the mass of the iron? 21.5 grams. What is the specific heat of the iron? 0.42 joules per gram C. What is the change in temperature? Okay, we only know the initial temperature. So that's Tf, what I'm going to call X here in just a few minutes, minus 100 degrees equals positive mass of the water, 132 grams. Change in temperature, X, same X. They're both going to arrive at the same temperature. That's what we're looking for. X minus 20 degrees C. And what is the specific heat of water? 4.18 joules per gram Celsius. All right, let's multiply our integers. 21.5 times 0.42. That's a negative 9.03 grams cross out, joules per C is all you have left, times X minus 100 degrees C. Equals a positive 132 times 4.18, 552 joules per C times X minus 20 degrees Celsius. Okay, we're running out of room here. Let's see what we can do. So let's distribute through. We're going to have to move up to the top and erase all this. Hope it's all right with you all. Okay, so 9.03 negative, oh, that's right, negative 9.03 x minus 9.03 times 100 is 903, and the C's cross out now, joules. And distribute the negative through, so that's a plus. So it's negative 9.03 x plus 903 joules. Okay. 552, and I probably should put the units there, joules per C. 552 joules per C x minus 552 times 20. 11,040 just joules, because the C's cross out. Okay, so probably the best thing we can do here is move the like, I don't know what they call it in math, but what I'm going to do is I'm going to add 11,040 to both sides. And add 9.03 joules per Cx to both sides. Okay, so that crosses out, that crosses out. So 903 times 11,040, no, not times, sorry, 903 plus 11,040 is 11,943 equals 552 plus 9.03 is 561 joules. This is joules. Joules per Cx. Alright, so we're going to need to isolate the x, so we're going to have to divide by 561 joules per C, divide by 561 joules per C. That means the joules cross out and the C becomes the numerator, which is good because that's what we're looking. So, 11943 divided by, cross your fingers, 561 equals, yes, an answer that makes sense. 21.3 degrees Celsius. I think we should have 3 sig digs. Yeah, 21.3 degrees Celsius. So, isn't that amazing? You're going to put a piece of metal that's super hot into water. That piece of metal plunges from 100 down to 21.3, and water goes up by 1.3 degrees. Amazing. Watch this.
9:46 on this Saturday morning. It's time for Imagine It, and I'm donning some really amazing wear here. Carl Nelson
Nice.
joins us.
All
Hi.
right. We got your fire retardant lab coat on, just in case. Mine is as well. We're going to
Okay.
talk about calories today.
All right.
Calories in food. Calories are not bad, they're just a measure of energy.
Okay.
And so I brought with me two different kinds of food. If you can grab a handful of toasted oats and just toss it in this little porcelain bowl, we kind of got one end of the spectrum of food there.
Okay.
Got some cheese puffs here. Oh, load that thing up.
Oh, load it up. All
We're
right.
going to load it up. What we're going to do is we're going to measure how many calories there are in each of these samples of food. Now, if we were food scientists, nutritionists, we
Sure.
would do this in a very careful and exacting way. We're going to do it really sort of down and dirty today.
No, no problem.
We're going
Just in the
to-
studio, right? No big deal.
Exactly. What we're going to do is we're going to burn these samples and we're going to measure or observe the flame that comes off. All right. Now, you could do that just by toasting them with the torch.
Okay.
But that's not going to be good enough. We need an excess of oxygen to get them to really combust well. And to do that, I brought with me, or I actually manufactured here, a little liquid oxygen. This blue liquid is liquid oxygen. It's about 2 balloons worth of oxygen. Far more oxygen than we need to combust this stuff. So here's the deal. I'm going to give you the torch.
Okay.
I know you're excited about
All
that.
right.
I'm going to pour the oxygen on the cereal. You're going to hit it with the torch, and then you should probably block your vision. Okay?
All right. This is going to be the end of the road for me,
All right.
folks.
Go ahead and light that thing up. Don't bring it over quite yet. Get ready. All right. Bring it over and hit them. Hit it and hold it there. All right.
Did I do it too soon?
No, that was great. So now you're getting a sense of how much energy there are in those
Wow.
toasted oats. They're really toasted at
Okay.
this point, right? Very, very still going. Very, very bright flame.
Yeah.
All right. Let's try it with the cheese puffs.
Okay. Now, do I need to hold it on there longer or a little bit less?
No, you did actually really well.
Okay.
That was pretty good. And, we don't want the smoke alarm to go off, so we'll cover that up. All right, so go ahead and light up your torch again.
All right.
So this is the comparison. This is the cheese puffs. Let me get the oxygen in there. Go ahead and hit them. Hold it there for a second. Okay, pull back.
Oh, wow.
Okay, see, that's why I brought the fire extinguisher as well.
Sure.
Incredible amount of energy coming off those cheese
You
puffs.
can feel the heat from that.
You can feel it. You can
Yeah.
see it. I'm going to cover some of these up here.
No big deal, Carl.
All right. There's a lot of smoke here now. But, I mean,
We have insurance.
the idea, excellent. I do too. The idea here is that there's energy in the calories.
Okay.
And I'm not suggesting you eat all cheese puffs all day, but it's just a measure of energy, okay? So the toasted oats are probably a better choice if you're going to consume just one of these two items.
Sure.
But they both have tons of energy in terms of calories.
And that's why the puffs burn longer, because they have more calories?
The puffs actually have a little bit of oil in them, so that
Okay.
helps them burn a little bit more, and they do have a few more calories. We kind of just did it really
Sure.
quickly here. We threw a handful
Not too
in.
scientific.
About 100
All right.
calories or so. But just calories, measure of energy.
Interesting. And
All right. So, question. If you were just worried, if you weren't worried about nutrition, if you were just worried about making sure you had plenty of energy, what would you go for breakfast? Toasted oats or cheese puffs? Hey, cheese puffs. Of course, you get absolutely no nutritional value from it. So, another question to you. Did you notice how he put out the flame? Most people would immediately go, well, if you put out the flame, then you use up all the oxygen. Probably not. Remember our demo. As that sucker is burning, the carbon dioxide being emitted is settling in below. It's more dense than air. So as that layer of carbon dioxide accumulates, it will eventually snuff out the flame because the combustible material can't have any more access to